Hello students, this is lecture 13 of MTH 201. In the last lecture we discussed equation of a tangent plane to a surface at a point and implicit differentiation and implicit function theorem. So today we are going to look at several examples of implicit function theorem. So let us recall the motivation behind this implicit function theorem. So consider the equation x plus 2y equal to 6 in x and y. So this is a line in the xy plane, right? And what is it in R3? If you have three coordinates, it is a plane, right? Because z is arbitrary. The variable y can be expressed as a function of x explicitly as y equal to 3 minus x by 2 for all x in R, right? And similarly, you can write x as 6 minus 2y for all y in the set of real numbers. So in this particular example, you are able to express each variable in terms of the other variables explicitly, right? So you're able to give me an explicit expression for a variable in terms of the other variable. Now you consider this equation x squared plus y equal to 1, again in x and y. Here you can write y as a function of x explicitly as y equal to 1 minus x square for every x in R, right? However, when you want to write x as a function of y, there are two possibilities, right? One is with the negative square root and other is with the positive square root, right? And if you look at these expressions, they are valid only when y is strictly less than 1, right? And if y is equal to 1, then these two expressions just gives you x equal to 0. But y less than 1 is something that is coming from this equation, right? Because from this equation, x square is equal to 1 minus y. Because x square is non-negative, 1 minus y should be non-negative, right? So therefore, y should be less than 1. Now the first expression is valid when x belongs to the negative x-axis, right? Because you have negative square root, while the second expression is valid on the positive x-axis, right? So the difference between first and the second example is that you have more choices for expressions, but you are still able to express one variable explicitly in terms of the other variable. Now, writing a variable in terms of other variables explicitly is not possible all the time. However, it may be possible to express a variable implicitly in terms of the other variables. We have looked at several examples in lecture 12 and we are going to focus on one particular um, example here as well. In fact, more. So let us see. So right now you understand the difference between explicitly representing a variable in terms of other variables and implicitly. So let us come to this particular example. We will discuss the examples in a minute, but let us recall implicit function theorem in R2, which we studied last time. So let capital F goes from R2 to R be a continuously differentiable function of two variables x and y. So what is continuously differentiable? It has partial derivatives and partial derivatives are continuous. So it's a differentiable function and partial derivatives are first order partial derivatives are continuous. Right? So you take a point x0, y0 in R2 and this is what we saw last time. that if the partial of f with respect to y at this given point is non-zero, then about this point x naught, y naught, the set of points xy which satisfy this equation is the graph of a differentiable function y equal to fx, right? Now, because you are on the curve, y naught should be equal to fx naught, right? Because that should be satisfied by this equation. And f prime x naught is minus of fx at x naught y naught divided by partial fy at x naught y naught, right? So this is what we saw last time. Now, with suitable change of variables, what you can do is just interchanging the roles of x and y. You have this statement. So, if the partial of f with respect to x at the given point is non-zero, then you can write x as a function of y. Okay, and you can see, you can compare these expressions here. You remember last time I told you that whatever is the derivative here, if it is with respect to y, you can write y as a function of x, and when you write this expression, fy, which is non-zero, comes in the denominator. Otherwise this thing won't make sense, right? Similarly, if fx, if the partial with respect to x is non-zero, then you can write x as a function of y, and when you take the differential derivative of this function g, in the denominator you get fx, which is non-zero. Okay, and here we are evaluating this derivative at y naught because this is a function of y, and here we are evaluating at x naught because this is a function of x. Okay, so it's easy to remember. We are not going to look at the proofs of implicit function theorem. If you take a course on real analysis 2, which is in the 4th year of um, mathematics major curriculum, you will see the proofs of this. We are going to skip it here, but you have these two versions in the case of functions of two variables. Okay. Now, in the function of three variables, you can have similar thing. Okay. So, if you have a function capital F, which is a function of three variables, a C1 function, and you take this level surface fx, y, z equal to 0, and you take a point on the level surface, and suppose the derivative of f with respect to x is non-zero, then you can write x as a function of y and z in some ball around x naught, y naught, z naught, and the now g is a function of two variables, so it will have a derivative matrix, right? The derivative matrix will be a 2 cross 1, I'm sorry, 1 cross 2 matrix because it's a function from R2 to R. The first entry would be the derivative of g with respect to y, and the second entry would be derivative of g with respect to z. With respect to y, the expression is minus fy by fx. Remember, in the denominator, the term which is non-zero will come, and the second entry, which is gz, is minus of fz by fx, and everything is calculated at the point x naught, y naught, z naught. But because g is a function of y and z, you will see y naught, z naught here. Okay. Similarly, if fy partial with respect to y is non-zero, then you can write y as a function of other variables, and you have similar expressions here. Note that in the denominator you have fy, and similarly if fz partial with respect to z is non-zero at this point, then z can be expressed as a function of x and y, and the derivative matrix is given by this. So in terms of remembering these expressions, it's quite easy, right? X, x, and x comes in the denominator. Okay, so that's how you can remember these expressions. Okay, and by the way, implicit function theorem is applicable in higher dimensions as well, and the statements are quite similar. So we are not getting into the statements at this stage. Okay, I'm sorry, the statements as well as the proofs at this stage. So let us look at this problem, which is problem number 8 from problem set 6. So the question is, near what points the level surface x equal to y square z square can be described as the graph of a differentiable function z equal to fxy, and what happens near the point 0, 0, 0 on the level surface, right? Okay. So now you want to see whether you can express z as a function of x and y, right? So first of all, uh, you will find a suitable capital F function, right? So we are looking at this level surface. So it is natural to consider capital F to be x minus y square z square. Then this level surface is nothing but the level surface of F at the value 0, right? Now, because we want to express z as a function of x and y, you want to compute the partial of f with respect to z, which comes out to be negative 2y square z, which will be non-zero provided y, this product, right, y square z or yz is non-zero, right? So I'm only going to focus on points when yz is non-zero. Therefore, by the implicit function theorem on R3, near the point xyz on the level surface with yz non-zero, the surface x can be described as the graph of a differentiable function z equal to fxy, right? So you are expressing z as a function of x and y. Now note that a point xyz belonging to S satisfies x greater than or equal to 0. Why? Because if you look at this equation, y square z square, which is the right hand side, is always non-negative, right? Therefore, the left hand side should also be non-negative. Also, in this particular case, you can express z as a function of x and y explicitly. So, you have an explicit expression for this little f. And what is that explicit expression? You just bring y square on the left and you compute z. Now remember that this explicit expression is only possible when y is non-zero, right? But if yz is non-zero, y will also be non-zero. Therefore, these are legitimate expressions. And the first expression is valid when z is positive, right? And the second expression is valid when z is negative. So you have these expressions which are working. Uh, there are two possibilities, one when z is positive, other when z is negative. Remember, z can't be 0 because then yz will be 0. So this is all coming from implicit function theorem, right? Now at the point 0, 0, 0. Now why is this a different point? Because at this point yz is 0, right? Both y and z are 0, so yz is 0. Of course, the partial of f with respect to z at this point is 0, and hence you cannot apply implicit function theorem. So IFT here stands for implicit function theorem. It is clear from the explicit expression of f that f is not differentiable at 0, 0. So you can check that this function that we have defined here is not differentiable at 0, 0. It is not even continuous at 0, 0, because if you walk along the line y equal to x, then the function is unbounded near 0, 0. Right? Okay. So because if y is equal to x, this is like 1 by square root x, right? And 1 by square root x, you know, becomes unbounded. So there is a problem at 0, 0, 0. You can't have an explicit expression or even implicit expression. So there is no possible expression that works out. Let us look at another example, which is problem 9 in problem set 6. The question is, can the level surface sin x plus sin y plus cosine yz equal to 1 be described as the graph of a differentiable function y equal to gxz near the point 0, 0, 0? If yes, compute the partial of g with respect to x and partial of g with respect to z at the given point. First of all, in such problems, we first construct the function capital F. Now, it is but natural to take capital F to be sin x plus sin y plus cosine yz minus 1, and then the given surface would be the level surface of S given by capital F equal to 0. Now, you want to see whether you can write y as a function of x and y, so you will compute the partial of f with respect to y, which comes out to be from taking the derivative of this, it comes out to be cosine y minus z sine yz. Now, if you evaluate it at 0, 0, 0, you get 1, which is non-zero. Therefore, by the implicit function theorem, there is a differentiable function y equal to this such that fx, you can replace y by gxz equal to 0, right? And this is near the point 0, 0, 0. Moreover, from the statement of the result, recall in the denominator you will have fy and in the numerator you will have these terms, right? If it is x, you will have x. With z, you will have z. You compute these terms, compute the partial derivatives, and this is what you get. The partial of g with respect to x at this point is minus 1 and with respect to y at this point is 0. Okay, so this was an example where you don't have an explicit expression. You have an implicit expression. Okay, so let us stop here.